Three, two, one, another 2070 video, and today we're hanging out with good old Graham and Schmidt. Alright, so, suppose we got a basis for a subspace. As we just saw in the previous video, it'd be great if that basis was orthogonal, because then we have a way of computing the orthogonal projection into W, which gets us the point in W closest to our original point. And as we mentioned, if I have a subspace that I'm really interested in being in, such as the column space, that would be great. Alright, but why does every subspace have an orthogonal basis? Right, I would probably need to explain how I could get that. Maybe a process named after two dudes. Okay. Alright, so let's go through it. Alright, so step one, we'll let W1 be X1. Note that trivially, if I let W1 equal the span of just that first element, then yeah, they're the same thing, and I got some goofy parenthesis thing going on here. Go ahead and fix that. And, yeah. There we go. Okay, so, alright, this isn't anything interesting or exciting. Step one of the process here, just don't do anything. Classic. Luigi wins by not doing anything. Alright, now we actually got to do something. So let's let W2 be X2 minus the projection of X2 onto W1. Right. Now, recall that projecting gets you into the perp, so W2 is in W1 perp, and that would then mean that W1 dot product with W2, which, note, would be X1 dotted with W2, would have to equal 0. Alright, W2 is in W1 perp, and W1 lives in W1. Okay, so hey, this gives you a way of quickly creating your orthogonal set based off of two things. Now, if we let W2 be the span of X1, X2, we know the projection is in W1, and W1 is clearly contained in W2, so we're in W2, and X2 by construction is in W2. That would mean that W2 is in W2, big W2, because the difference of them is a linear combo. So W1, which is X1, has to be in W2, and so does little W2. So they're both in there, and since they're linearly independent, they have to coincide with the span, right? The span of these two elements gives me a two-dimensional space, and so if I've got two linearly independent things spanning the same set, they have to be the same subspace. Alright, so here we see that I started with two elements, X1, X2, and then I figured out how to create two elements that are orthogonal and have the same span. Let's see if we can go for 3. Do the same thing. Take W3 and look at X3 minus the projection of X3 into W2. By construction, this is in the perp of W2, so it's in the perp of the span of W1 to W2. So that means all of our dot products have to equal 0, so I have again created a orthogonal set. Okay, so nothing new or exciting there. Okay. Now, the real money here is to show that W3, being the span of X1, X2, X3, would coincide with the span of W1, W2, W3. That would mean that at each iteration here, I'm making a bigger orthogonal set, but I'm not changing my spans, so in the end, I'll get a basis for W. Alright, let's say that we actually get that W1 and W2 and W3 span that. Well, W1 and W2 were in W2, big W2, so they have to be in W3, because W3 is just extending it by one more element. Alright, so I just need to figure out why W3 is in W3, little W3. Well, the projection's in W2, so it's in W3. X3 is W3, so the difference is in W3. So there we go, all three of our elements are in W3, and they're all linearly independent, so they have to form a basis, because W3 is three-dimensional, I have three linearly independent things, they have to fill up the space. Alright, And as I mentioned, you would then repeat this until you got up to AWM, which would be all of W. So we have just justified that indeed, if I have a basis for a subspace, which a subspace always has a basis, then you can orthogonalize it. You can turn it into a W1, W2, all the way to WM, and what you end up with is orthogonal, and it spans the original space. And that's everything we just discussed in a neat little package. So if you got a basis for a subspace, you can orthogonalize it by going through the process of looking at x1 first, then taking x2 minus its projection into W1, then taking x3 minus its projection into W2, so on and so forth. This is the content of the Gram-Schmidt process. And there are the wonderful little formulas there. So again, what you're doing is taking your original element, x1, then you are creating a next element by projecting the second element into the subspace spanned by W1, and then you repeat that process. Sweet. Okay. So now we know that I can always orthogonally project into any subspace, which is what I want. But you got to compute the Gram-Schmidt process, so let's do a couple of them to get a feel for it, and then we'll call it a video. Alright, so let's create an orthogonal basis for this. Note those two elements are not orthogonal. Their dot product is equal to 1, not 0. Alright, well W1 is always taken to be the first element, and then I can create W2 by taking my second element and subtracting its dot product with our first element, divided by the dot product of that element with itself, times that element itself. And then we get a negative 1/2, and that's got to be an orthogonal basis for W. And you can check that this indeed is orthogonal. Take the dot product, you will get 0. Hey, there we go. Sweet. Alright, well, 2 ain't enough, I need 3. And that's as far as I'll ever go. And as far as I'll ever make you go as well. So what do you got to do here? Well, you got to create your W1, which is just pick your first element. Then you create your W2, following those formulas. That's the computation you end up getting. Note, W1 and W2 are perpendicular. Take their dot product, you get big ol' 0. Then you got to get your W3, and following the formula, this is all the computations you got to do. So note, you've got 1, 2, 3, 4 dot products to do, and then you got to do scaling twice, and then you have to add it all up. Alright, and then you end up with 0, 1, -1, and you can verify indeed the dot products of all of these things are in fact 0, so you do have an orthogonal basis. Great. There's the Gram-Schmidt process. No more, no less, that's all it is. Alright, now obviously computationally it gets pretty involved, but as we are going to see, this is incredibly powerful because now we know that we can always project ourselves into any subspace that we want. Right, so we sort of set up last time that this is theoretically possible, as long as you have an orthogonal basis, but now we know that indeed you can always create one. Great! So, how about we project ourselves into the column space? That sounds like a great idea.